Okay, so now let's benefit from this last hour. Let's construct graphs, which are actually very natural graphs, by using groups. So that was like a very short introduction to characters or finite abelian groups. Now let's benefit from Cayley graphs. Now actually Cayley graphs. What's a Cayley graph? So you give me a group. It doesn't have to be abelian, by the way. The construction of LPS and the I told you is of non-abelian, but we are going to abelian. So let G be an abelian group. Finite. So the graph that we are going to have, which you cannot call G now, but we call it K, GS, has this extra thing S. Okay? So the vertices of the graph are going to be G, but the edges are going to depend on a choice that you have. You can construct many graphs from a given group. Okay? So the way you do it, so let F be any subset. Doesn't have to be a subgroup, just subset, not subgroup. You don't probably know what subgroup is. Just a subset. It doesn't have to be closed under multiplication. Okay? But I assume that it is closed under negation. You'll see in a second why. That if S is in X, then minus S is in X. Well, minus S is really just the inverse. Why the inverse? Just inverse. The thing that you multiply to get 1 or add to get 0. Yes. Like this, exactly. Oh, yeah. Okay, so you have a set of some subset of the elements, to be really arbitrary set, and then you define the graph as follows. So as I said, the vertex set is G, the group. You have an element for every group, and the edge sets. Well, to tell you the edge set, let me tell you who are the neighbors of G, little g. So the neighbor set of little g, we use that notation already. Neighbors G is G plus S. This is the group plus, okay? In abelian groups, it's actually nicer to have the product written as a sum because it kind of reminds you it's abelian. Yeah. That's it. So the neighbors of an element in the group vertex is, you add S to it, still lands you in a group element, and that group element is a neighbor. Okay? Are those be distinct? They will be, yes. Otherwise, it won't be here, right? Or maybe might be. It's fine, yeah, you can. So if you have like double edge, it's still fine for regularity if you count it twice. I think, particularly in this case, it will be like distinct because G plus S cannot be G plus S prime unless S equals prime. Because you can take the inverse of G and G. Right, so if G plus S, so this is the S neighbor, and this is like G, some S prime neighbor, then by subtracting G and then adding minus G, the inverse of G, you get the S equals. So actually these elements will be distinct, but it's fine if they work. Happens in graph that we use that you have multiple, and you still very well because you just count it twice if you get it work. And like the ability to learn in the same spot is bigger, right? Like you don't work on it. Yeah, that's true. You better not do that. That's true. That's a good point. But sometimes in the construction that you have, you just have it, and you don't know how to make something better without. Yeah. But you're right. In general, that's not a good phenomenon. Yeah, that's a good.
S is not necessarily a subgroup.
Right. It's not necessarily a subgroup, just a subset. We'll see two examples in a second. Or one of them, there won't be subgroups. But you see why I required S to be this property? In terms of the graph, I mean, what would have happened otherwise? The directions, right? So here what we are again, so this is a vertex, some group element, and its neighbors, I told you, are G plus S. But I mean, I should be careful because there is another G plus S here or whatever. But why is this his neighbor? Right? I mean, for this to be his neighbor or its neighbor, you should have some element in S that when you add to that, you get G bar. So that's minuses. And that's why you need. You can talk about directed Cayley graphs also. I want undirected Cayley graphs. So this is for the undirectedness. That's a word. Good. Do you have like 2 minutes to? Ah, 10 minutes. Oh yeah, that's PS. Right. No, so let me give you the 2 examples. It's actually let me give you 2 examples of Cayley graphs that you know actually, but I haven't thought of them as Cayley graphs. So example 1 is the circle, the cycle. For length n cycle. What's going on here? Length n cycle, I mean. So you know this graph, right? I mean, I don't know if you see it, right? You see it sometimes. This graph. But they claim it's a Cayley graph. So what do you think? What's the group is like? What should you do? Z5, exactly. Or like Zn, and what's the set of generators? So this is the group. So maybe let me write it as the cycle of length n is the Cayley graph. The vertex set or the group is Zn, and now you see you have 2 elements in S, right? That's for sure. 1 minus. So if you write it as 0, 1, 3, 4, and 5, you see that when you take S to be this thing, you get the length n. In general, if you have a graph with many kind of symmetries, it might be a Cayley graph. That's kind of you see a Cayley graph, from every vertex, you kind of see the same thing. Its neighbors are different, other vertex, but in a sense, they're also the same. The only difference is where you go at, but the instruction add F is the same regardless of the vertex. So from here, you know what the neighbors are. You just add and subtract minus 1. Also from here. So it's really symmetric and nice. It's really useful for, as you see, for understanding the eigenvalues and eigenvectors. Okay. Okay, so the second example is the Boolean cube. So that's just the graph before Cayley graph. Just the graph that looks like that. So this is the 2-dimensional Boolean cube. This is the 3-dimensional Boolean cube. And the way I think about it is this element has name 0, 0, 0, 1, 1, 0, 1, 1. You know, this is 0, 0, 0, 1, 1, 1, and so forth. But like formally, the vertex elements are vectors in N, binary vectors, and you have an edge between 2 vectors if they differ in exactly 1 entry. Right, so here you don't have an edge because they differ in 2 entries, but here you do have. Right, so this is if you know the Boolean cube, that's how you know it. But the definition of it as a Cayley graph, so the Boolean cube sometimes denoted by H for hypercube. Hn is the Cayley graph obtained from, okay, what's the group?
That's like this. C2.
Right. But let's do it like that. Right? And okay, what is the set S of they're called generators by the way. What are the generators?
The flat minus.
Very good. It's Boolean, so it's good. So I don't need to take the minuses, that's a good point. Because the characteristics too. But good, so E1 is enough. Because my E1s is bad. But these are exactly the set of generators, right? What is EI? This is the like a how do you call it? The standard basis. Yeah, right. Who is it? Forget the name. The unit vectors, right? Standard basis. Unit vectors. The unit is like a yeah. Unit sometimes can be sound like a vector of unit size. They are. And you see why, right? Because every element here, take any vector. When you have n neighbors, like here you have 2, here you have 3, the dimension neighbors, and these are precisely those when that are different by you by 1, precisely means you add one of them. Just change one bit. Good, so we know Cayley graphs, even before we knew Cayley graphs. We knew that there are Cayley graphs. And now in the last 5 minutes, in the punchline, then we'll take break. The punchline is that the eigenvectors Cayley graph are the curve. It's one line thing, but it's really nice. Then after the break, we'll do these 2 examples. So
Yes,
physics,
maybe 1 hour.
what? 1 hour. Well, let's create a theorem. Let's elevate it to a theorem. So let G finite abelian and S goes under negation, inverse, same thing. When you talk about abelian groups, you look at negation. Then the eigenvectors of the Cayley graph, and when I mean eigenvectors of the Cayley graph, I mean of the adjacency matrix. Graph has no eigenvector, it's a graph. And look at the adjacency matrix, when that has an eigenvector, and these are the eigenvectors of the Cayley graph. Very good. It's amazing, an amazing fact, good observation. Amazing fact that the eigenvectors do not depend on the choice of generators, yes? But the eigenvalues will. So all of these graphs have the same eigenvectors, which mean they commute, by the way, can you multiply them? But the eigenvalues of those will depend on this choice. So it's a crucial fact. Observation, because of the eigenvectors are properties of the group, not of the set of generators. The group only. Very useful. You like to have like a steady set of eigenvectors. Move around. Take another graph. That's one reason why they're so useful. So let me just move like the 119 and then you come back and for example. Also in the proof, we'll actually see what's the eigenvalue. I mean, I should technically tell you in the proof statement, the theorem statement what's the eigenvalue. I don't know. I need to do the calculation and see.
Yeah. The eigenvalues are the ones that matter for the
Right.
omega and the E.
Exactly. But the eigenvectors, if you understand them, you have a better chance to understand them. But you're right, you don't need the eigenvectors. Well, so let's, as usual, denote by A, the adjacency matrix of the graph. And let's look at A carry. So we have fixed carry a character. And I want to show that carry is an eigenvector. I think it's also eigenvector of the adjacency matrix. So I just need to multiply them and see what happens. Particularly, I'm evaluating in particular entry G. And I want at the end to see a number times chi of G. Right? That's how it works. The same number independent of G. Number times the chi of G. Okay, but okay, so what how does it work? So A no, A times V, G, I need to go over all neighbors of G and add chi, whatever vector sits here, add that point. Right, so this in general, right? AV, when this is an adjacency matrix, maybe it's called A star. A star of some vertex is you go over all neighbors of the vertex, psi of U. Because you have ones exactly where you have neighbors of it, in general. So here, just because I don't want it to look weird, here the neighbors are just plus S. So you go over all S in F, chi of G plus S. Because that's the neighbors, they have a very specific form. They are all the shifts by S. And that, you can write, well, that, you can write as chi of G. And now you're happy because the chi of G goes out. You get here the eigenvalue. This is the eigenvalue, really.
And it's independent of S.
Independent of G. The chi. Right, the eigenvector are independent of S. And the eigenvalues, I mean, that's a number that's independent of G, that's important. So it will be the same number for the vector. Because you want a number size a vector for all entries of the vector. So let's call this lambda of I. So this is the eigenvalue corresponding to the eigenvector. The eigenvalue corresponding to eigenvector. But you see, it does depend on S, of course. Something must depend on S, but it's not the eigenvectors, it's only the eigenvalues. And after the break, I think. When does the break? Yeah, exactly now. After the break, we'll compute using that, we'll compute the eigenvalues of the cycle. I mean, it's hard to compute in general eigenvalues, but here it's a very easy recipe. If you know the characters, it's a very easy recipe. Compute the eigenvalues of the cycle and the boolean cube. In the homework, you'll do one more, 5. And then we'll do zigzag. By the way, for the zigzag, I'm using a presentation. I have one, and it's really good. From another course. So it's on the website if you want to look at it now. But I use like slides. Okay, so let's continue. So before the break, we talked about Cayley graphs, and you said that if we have a group and a set of generators, which is closed under negation, then the characters of the group, regardless of S, are the eigenvectors of the graph, and the corresponding eigenvalues, unless I remember it correctly, is different. So the eigenvalue corresponding to lambda 3 or chi, depending if you're Israel, is the sum of yes. And that does depend, of course, on the sequence. So let's see some examples to see it in action. 2 examples. So the first example is, of course, the Cayley graph of Zn with the set of generators plus minus 1, which is just a cycle of length n. And okay, so we said already that the the characters, which are the eigenvectors, well, of this group, well, you have 1 for every element, for every integer between 0 and n minus 1. And now we also know there are most n of those. We actually proved that the character set size is most dimension, which is n. And we said that this function or vector, depending how you want to view it, at a given element, so as a vector with 3k as coordinate l, as a function is 3k applied to l, that's just omega n to the kn. Let's remember that those were the characters. Okay, so from that, let's compute the eigenvalues. So that's the eigenvector basis. Maybe for example, let me just, I don't know, if maybe in Z4, which is the easiest one right now, and in the case of n equals 4, right, so this is the length 4 cycle. It's actually, this graph is many things. It's the length 4 cycle,
Minus I 1.
Okay.
No, it's not a 1, it's a minus I.
Minus I squared. I times I is minus 1. It's
minus 1.
minus 1, even this one.
And I.
No, flip the wait.
No,
no,
that's the correct sign. Okay.
I checked that it's orthogonal to that. And the sum should be 0.
Because we wanted it explicitly like
Yeah. I just giving them explicitly so that you can.
okay. Just like the eigenvalues are just like
Right. So these are the eigenvectors. Right. So this is the eigenvector corresponding to this character, and that's the last one. I just wanted to write it one time explicitly in some example, but the eigenvalues now, in general, even regardless of that. So what are the eigenvalues? This is just like a double C4 so that you have it. For a general n, right? The eigenvalue corresponding to one of the characters, k. Right, I'm taking one of the characters. In general, it's from 0 up to n minus 1. Well, by the equation there, I need to sum over all possible generators. In our case, there are only 2 generators. Somebody's like, something will happen on the board. Was I the only one to see that?
The projector
Projector
next
started.
to the A mode.
Oh, I see the real. I see.
so twice the real
Right. So I need to write the sum of all generators of this applied to each of the generators. So it's chi k of 1 times entry lambda k of, oh, I'm confused once again. Of 1, yeah, right? Plus chi k of minus 1. And then summing over all possible generators, the evaluation of the character on that element of the generator, on that generator. But we know what these are. Like this is chi k of something is omega n to the k is times the something times 1 plus omega n to k times minus 1, which is just twice the real part of omega n. These are the conjugates of each other. Which, if you want it in terms of like cosines and stuff. Okay, right. But it's the real value of this. So you see, like it's really kind of weird in my head.
It's without the I in cosmos, right?
Yeah. That makes even sense. It's e to the I, with the real value of e to the I over n, k over n. Okay, that's cool. We have like an eigenvalue, right? Like, so think of it like, where does it go from? So k starts from 0 up to n, not including. So if you draw down cosine it's like that, this is like 2 pi, so you don't get here. Right, you jump in multiples of 2 pi over n. Like 0 up to this thing which you never reach. This is like pi. And what do you see? So for example, you see that if n is even, then k, you can take k, which is n over 2. And so there is an eigenvalue, the middle one, it's like -2. Like it's 2 cosine, it's twice the cosine. So if n is even, there is actually a character, which when then the corresponding eigenvalue, which hits -2, which makes it a very bad expander. Because omega is like d2 is the degree. You want omega to be much smaller than the degree. Here the degree is 2. You don't have like too many.
Oh, it's the bipartite.
Right, exactly. Good. And what I told you last time, like in a small notation on the board, we were proving it, is that the graph is bipartite if and only if there is an eigenvalue which hits -d. And indeed, when n is even, it is bipartite. You can take every other vertex. And when n is odd, it's not bipartite. And indeed, when n is odd, you don't quite hit -2. You can take k over 2. You can take it n -1 over 2 with a sum over 2.
But what we can see is that for a large enough n, we are close to the.
Exactly. So good. So that's one thing. So when n is even, you get that omega is like 1. Then there is an eigenvalue that hits the degree, an absolute value. It's bad. But but that's equivalent to being bipartite. So I don't know what it means. It's bad. It's just what it is. Now, when n is odd, then it's still not a great expander, because you can take the second largest eigenvalue, or maybe you can take the second from the minuses, but it's the same thing. The second one,
Actually, it's closer to pi.
here when it's closer to here.
Yeah,
Okay.
because it's half the distance.
Right, that's true. That's true. So here it's like I compare in 1 against n minus 1 over 2, so it's half. You're right. So when n is odd, so omega, the worst possible k you can choose is the one which you take, say, n minus 1 over 2. Oh, sorry. You can take k, which is n minus 1 over 2, and then what you'll see there is like 2 cosine of whatever 2 pi. It's roughly okay. It was easier when it's 1 divided by n. But then what's really important for me is that I don't know if you remember that, but cosine. So okay, let me take k equals 1. It's almost the same thing, and then I have a 1 here instead of that. Okay, just because it's like easier. Because that's a small number now, I can shift by pi.
It's just the factor of 2 and the factor of minus on the outside.
Right. But let me still do it this way. Then that's you see 2 pi over n, but in general cosine of x is right. It's that stuff, but it's roughly this way.
But you can remove the 2.
Right. Okay. Still. And so what I care is asymptotic, so I don't really mind. So what you can see is that omega is roughly 1, so it's exactly 1 minus some constant times 1 over n squared. And the constant, you can get a twice as big constant.
Is it times 2 times that?
Oh no, because omega is nowhere. Right. Omega is nowhere.
No, the constant is 4 times better when you take n minus 1.
But what I'm saying is that the gap is very bad. I mean, I want omega to be far from 1, and here it's like quadratically close to 1. Not so good. But you know, that's what it is. It's fine. I mean, what do you expect of degree 2, right? It's like every graph of degree 2 is a cycle at best. It could be like a union of cycles, which is disconnected, which is worse. So that's the best thing you can do. For degree 3, you can do stuff. That's what we said. If you think about it, 2 square root v minus 1, when d is 2, gives you 2. When d is 3, it gives you 2 square root of 2, which is much more. When you flip it that way, that's what smaller. It's not so small. Like when d equals 3 here, you will get like 2 square root of 2, which is smaller.
We get an odd degree if you take plus and minus.
No, right, okay, not for this now. No, in general, I mean, if you take a Cayley graph, for example, the second example, the Cayley graph with degree, which is 3, you can hope to gain some. But for degree 2, you just can't because just because you know all graphs of degree 2. It's a cycle if it's connected. Or it's a path if it's not if it's even worse. If it's not regular, you get most. The second example is better but not good. So we had the Boolean cube. Right, so the Boolean cube we had, so we called it Hn, and it was Z2 to the n.
Is it bipartite again?
Yes. But other than that, you're right. Good point. It's still bad. It's always bipartite. You're right. It's actually worse. Always. Good point. But at least that's a one-sided expanded step. So the omega 2 is bounded away from 1. Omega n is going to be minus 1, which is bad. You're right. Regardless of degree. But omega 2, which you're going to compute now, it's going to be still close to 1, but not in that rate of convergence to 1.
Didn't we say omega 2 is 1/5 with the graph in the bipartite?
No, that's omega n.
Omega n is always
Right.
1/5 the graph in the bipartite.
Yeah. Omega 2 relates to the edge expansion. So if you are disconnected, it's 1. Omega 2 is yeah. Omega n kind of measures the cyclicity, and omega here you have only cyclicity 2, and omega n the connectedness. Omega 2 the connectedness. But let's do that. It's a good exercise to see this. So we're looking at this graph. It's bipartite. So right, omega n is minus 1. But let's do omega 2. Or let's do everything. What are the, so we said that the characters, right, for every n, technically n bit string, really, you have a character. And the character takes an element in Z2 to the to minus 1 to the UIPI. Should sum. Because it's really the product of the characters of the individual groups. Should sum it in the other way. Product is, so in my head, it's like that. I should take the product, which becomes a sum in the export. So is that just, we did it before. We talked about it in the previous lecture. So this is just a reminder. It's not completely obvious. We talked about it. And okay, so now maybe I'll stick to this board. Let's look at the eigenvalue lambda corresponding to some V, chi V. So we know what we should do. Let me write lambda against the chi V. The eigenvalue corresponding to this. So you should take the sum of that expression across all the generators. That's what I should do. I should do the following. I should sum. The generators are just unit elements, unit vectors. Right, I should just take the sum of all the generators, but the generators are VIs, unit vectors. But then you see that chi V of a unit vector, that's why I wrote what I wrote before. It's just VI. I mean, this thing is just minus 1 to the VI. Because VI only picks the VI entry. So you have a sum, but this thing is just E minus 1 to the VI. Because the technically inner product between EI and V is VI. That's good. So you can immediately see that the eigenvalue corresponding to the all zeros vector is n. N is the degree, so it makes sense. It's n. And as you said, the eigenvalue corresponding to the vector for the all ones vector is minus n, because everything is minus. So it's bipartite, so we'll work over is bipartite.
Wait, the lambda, but like you need to normalize it by the side of the group. The lambdas.
To get the omegas.
Like the omega.
Right.
Isn't the size of the 2 to the n?
Yes.
So aren't you gonna get n over 2 to the n, which is not -1? Negative n
Uh,
over 2 to the n?
No, sorry. These numbers you shouldn't. Okay, these scale not of the number of vertices, but of the degree.
Ah, okay.
Good. But still, okay. So again, lambda v is n, which is the degree. Lambda, so lambda 0, like all zeros is n. Lambda all 1 is minus n. And if you want to find an eigenvalue which is large, but not on these extremes, what would you take? There are many options, like 2 end options. So what give me a v which determines lambda 2?
1, 1, 0.
Okay, so I'll leave in 1, 0, 0, 0. Let's see.
One.
Right, 1, 1. Not 1, 1, 0, 0, 0. Good, yes, exactly. So let's take lambda of a unit, any of them, a unit vector. And you can also take the complements. That's what you have like 2 and n of those, and use the complements, less than is 2. But lambda ej, right? You get everything is a plus except for 1, which is a minus. So it's actually n minus 2, right? Because you have n minus 1 ones and 1 minus 1. When you move something from one set to the other, it contributes 2. Because you take 1 from the ones and add 1 minus 1, other minus 1. Okay. And actually you have many of them, right? You have n of those, and you can generate like n choose 2 things with n minus 4. And so you can actually find the entire spectrum point easily. But for us, that suffices. What's omega 2? Like not omega n. Omega is 1 because the graph is number. But as you know, for one side of the expanders, we care about omega 2, and omega 2 is 1. I should just value. Exactly, which is 1 minus 2 over n. That's still bad, still close to 1 as n goes to infinity, but it's much better than that. Because n is not the size of the graph, it's the degree. So that's 1 minus 2 to the log the size of the graph, right? The log of the actual size of the graph. So this approaches 1 in a logarithmic place, like 1 over log place, whereas the cycle did it in our like 1 over square size of the graph place. Much worse, like exponentially worse.
But something bothers me because like it's a regular graph, right?
Yes.
And the degree of each node is like
n.
n.
Not exactly. The graph size is 2 to n. We deviated from our usual notation of n. That's right. So the graph size is 2 to the n.
Okay.
Right.
So it's logarithmic.
It's logarithmic, right? So it's still bad. It's not good. It's still close to 1 and goes to infinity. We want something that's close to 0 because the degree goes to
And
infinity.
also d increases as it goes to infinity.
Right. But here the degree goes to infinity and the expansion goes to 1. Like it's bad. But you know, that's okay. This was not meant to be an expander, just nice graph. That's it.